This continues the lectures on projectiles. Let me now go ahead and take a look at some more specific examples. In the first example that I did in the prior lesson, we fired a projectile horizontally. Now let's fire a projectile on an angle. We'll launch the projectile from the ground, and we're going to calculate out here a number of different quantities. Okay, let's go ahead and copy down the first of the problems associated with this lecture. Let me go ahead and read it to you now. A projectile is launched from the ground at a 30-degree angle with a speed of 100 meters per second. In part A, we're going to calculate the maximum height reached, and then parts B and C are going to go together when the object eventually returns back down to the ground. There is a part D. We'll get to that, however, in a few minutes. Let's take a look at part A first. Okay, so we launch our projectile like so with an initial speed V0 of 100 meters per second. Okay, let's go ahead and visualize the components here of the initial velocity vector. Right here is the projection angle. The projection angle theta naught is given to us as 30 degrees. Because we are launching from the ground, let's immediately assume that we're launching the projectile from the origin. So horizontally, the initial position x0 is equal to 0, and vertically, y0 is equal to 0. Okay, and then in part A of the problem, we're examining what happens when the projectile reaches its maximum height. So the projectile moves through its trajectory like so, and then right here at this instant, this is when it's at its maximum height. Now at that instant, what does the instantaneous velocity vector look like? Well, the instant that the projectile reaches its maximum height, the instantaneous velocity vector is horizontal. It looks like so. This then means that the y component of this instantaneous velocity vector when the object reaches its maximum height is equal to 0. So v sub y is equal to 0. And now here in part A of the problem, we're going to calculate out actually a couple of different things. The first thing we're going to calculate out here is the maximum height y. That's the final vertical position. We're going to need the time t, however, to do so. And then just for a comparison that I'm going to make a little bit later on in this problem, I'm also going to calculate the horizontal displacement x, that is like so. Okay, now let me immediately write down my projectile kinematics equations. If you recall from the previous lecture, they are as follows. First of all, in the vertical direction, we have the position equation. Still in the vertical direction, we have the velocity equation. And then in the horizontal direction, of course, recall that there is no acceleration for a projectile, so then therefore the position equation horizontally looks like the following. And then horizontally, the component of the velocity vector v sub x is equal to a constant. Recall, of course, that g is acceleration due to gravity in metric SI units. It's 9.8 meters per second squared. Okay, let's begin to analyze part A of the problem in the following way. Because at the instant that the object reaches its maximum height, the y component of its velocity vector is equal to 0, let's actually begin our mathematical analysis of the problem by using this expression here, where we'll set the left-hand side of the expression equal to 0. Like so. And then if you look carefully at the resulting equation, you'll notice that the only unknown is the time t, which we can now solve for. So let's go ahead and solve for t. So to do so, I move the gt here to the other side, and then divide the g to the other side to get the time t by itself, like so. Okay, now in degree mode on your calculator then, let's go ahead and calculate the following. First of all, the numerator of the expression. The initial speed 100 and then multiplied by the sine of 30 degrees. Recall, by the way, from basic trigonometry that the sine of 30 degrees is equal to 1/2. And then we'll go ahead and divide by 9.8 meters per second squared, and this gives us a time now of 5.1 seconds. And now that I have that time, let's just go ahead now and calculate directly y, the maximum height reached, by plugging in all the values here on the right-hand side of the expression. There's no algebra to perform here. We already know everything on the right-hand side. So let's go ahead and now calculate y. So we have, first of all, y0, which is 0, and then the middle term. So 100 times the sine of 30, and then multiply then by 5.1 seconds. And then minus 1/2 times 9.8 times 5.1 squared. And ultimately, the maximum height reached by the projectile is about 127.55 meters. Okay, and then for a comparison that we'll make in parts B and C of the problem, as I mentioned earlier, let's also calculate the horizontal displacement x. In order to do so, we'll just plug everything into the horizontal displacement equation. We know everything on the right-hand side of the expression. So let's go ahead and calculate this. So first of all, we have x naught, which is 0, and then I have 100 times the cosine of 30 degrees, and then multiplied by 5.1 seconds. There we go. And this works out to be about 441.7 or so meters. And now let's move on to parts B and C, which go together. And when we do, we're going to see some very obvious symmetry occur. So let me begin to draw out parts B and C. Okay, so for parts B and C, we're going to once again launch the projectile from the ground. So here's the initial speed. Here are the components of the initial velocity vector. Here's the projection angle once again. And then we're launching once again from the ground, so both x naught and y naught are 0. And now we're taking a look at the projectile's entire path when it returns to its original height. That is like so. Okay, and then the instant that the object does return to its original height, its final vertical position y is equal to 0. And then here's what we're going to be asked to calculate in part B of the problem. First of all, we're going to need to know the time t over which this occurs. And then right here is the horizontal displacement x. This horizontal displacement is referred to as the range. The range refers to the horizontal displacement when the projectile returns to its original height when it returns to the ground. A little bit later on in part C of the problem, we're going to take a look at the details here of this velocity vector v. The instant that the projectile returns to the ground, we're going to look at the x component, v sub x, and the y component, v sub y. Okay, but now let's make a comparison here in terms of symmetry. So for example, in part A of the problem, the time necessary for the object to reach its maximum height was 5.1 seconds. Take a look at just the diagram itself. What do you suppose the total amount of time is going to be when the object goes from here to here? If you are intuitively guessing that the total time is going to be 10.2 seconds, you are in fact correct. Let's take a look then at the displacement. The displacement x, for example, on the top board horizontally was 441.7 meters. What do you suppose the range is going to be here in part B of the problem when we calculate it in just a few moments? It's going to be twice 441.7 meters. If you intuitively guess that, you are in fact correct. And the reason for this is because pretty obviously the path that is traced out by a projectile is a parabola. I will prove that, however, at the end of the problem. For now, we do in fact have to calculate these values. Okay, here's then how we calculate the time t and then the range x. Okay, we return to the ground. So the vertical position y is equal to 0. Let's begin the mathematical analysis by taking a look at the vertical position equation. So here's the vertical position equation, and in the equation, two things are equal to 0. We have the final vertical position and the initial vertical position. So let's go ahead and plug in our zeros into that expression like so. Like this. And then if you look carefully at the expression, you'll notice that the time t is the only unknown, and we can now in fact solve for it. Technically speaking, however, it is a quadratic. There are two solutions. One of the solutions for the time t, however, is 0. Notice that 0 minus 0 is equal to 0. And this actually makes sense because at times t is equal to 0, the object here is at its initial height of equal to 0 at time 0. However, we don't care about that time. We just want to solve for the other time. So let's go ahead and do so. In order to solve for the other time, because this is 0 on the left-hand side of the expression, I can go ahead and safely cancel out a t here from each term like so. And now we just solve for the remaining time. So let's take this 1/2 gt and move it to the other side like so. Okay, and then cross multiply the 2 and the g over to the other side, and then that then gives us the time t. So, and now if you take a look at this expression for the time t here carefully, which we found from this position equation, compare it to this time here that we used the velocity equation to derive for part A of the problem. Notice that this value here is twice as much, so then therefore the total time is, as you may have intuitively guessed, 10.2 seconds. Okay, this immediately allows us to calculate now the range. So take a look at the horizontal displacement equation and recall that x naught is equal to 0. The only thing that's changed from part A to part B of the problem is that we've doubled the time t. So if we double the time t, we then therefore double the value of x. So then therefore the range is twice this value here. That value is 883.4 meters, like so. You do have to calculate these values here. You can't just automatically assume the symmetry in the problem, even though in fact, yes, the trajectory here of a projectile is a parabola. I'll get to that once again when we finish the example. Okay, now for part C of the problem, we're asked to calculate the details here of the final velocity vector v. Let's go ahead first of all and find the x component v sub x. Recall that the x component v sub x is the same thing as the initial component in the x direction of the initial velocity vector, because once again recall that there is no acceleration for a projectile. So let's go ahead and calculate it directly by using this expression here. Okay, so v sub x is going to be v naught, which is 100, and then multiplied by the cosine of 30 degrees. That works out to be 86.6 meters per second. And now using this time t right here, let's go ahead and find the vertical component of the velocity vector by plugging in everything here into the right-hand side of that expression. Okay, let me clean up my board here a little bit before I do. Okay, so let's go ahead now and find v sub y. So using the second expression on the board above, 100 times the sine of 30, and then minus 9.8 times 10.2, and this works out to be negative 50 meters per second. Now in component form, this final velocity vector v can be written in the following way: 86.6 I hat minus 50 j hat meters per second. But let me do a little bit more symmetry here and calculate two more additional things to finish part C of the problem. Let's go ahead and find the final speed v. I'll do so by doing a little bit of Pythagorean theorem with these two components. So using some Pythagorean theorem, 86.6 squared plus 50 squared, and then take the square root of that. That ultimately comes out to be a speed v of 100 meters per second. Notice that the final speed of the projectile is the same as the initial speed when the object returns to its original height. That has something to do with what is called conservation of energy, which we'll get to in a later unit. Let me also go ahead and calculate this angle here. I'm going to call it theta. I'm going to find that angle by doing a little bit of tangent. Okay, let me do a little bit of erasing here before I do. Okay, the tangent of that angle theta is going to be the opposite side of this vector triangle, v sub y, divided by the adjacent side, v sub x. It is in the fourth quadrant, so I'm going to get a negative answer here, and that's perfectly fine. But I do now take the inverse tangent then of negative 50 and then divide it by 86.6, and sure enough, that angle turns out to be negative 30 degrees. Once again, like so, and recall, of course, that the projectile was launched at a 30-degree angle. You're seeing all of this symmetry here, as I've said before, because the projectile's trajectory traces out a parabola. Once again, I'll get to that later. There is, however, before I do so, a part D to the problem. Let's go ahead and take a look at that. I have to move my file. In part D, it says, when and with what velocity is the projectile at a height of 10 meters above the ground? Let me do some erasing. Okay, so for part D now, what we're asked to take a look at is at a specific height. So let's say that right here is when the projectile is at a height y of 10 meters, but then also on the other side here, like so, over here, it's also at a height y of 10 meters. So I should calculate two times, once on the way up, if you will, and once on the way down, for the projectile to be at this height. Now we're also asked to take a look at some details of the velocity vectors at these heights, or at this height rather. Right here, the velocity vector v is going to look like so, with its x component and its y component. And then here on the way down, here's the velocity vector v like so, with its x component and its y component like So we'll see some more symmetry associated with these components here as we proceed. Okay, now here is in fact how we mathematically proceed. Because we are given the final vertical position y of 10 meters, let's go ahead and begin by looking at the vertical position equation. Over on the right-hand side, the initial position y0 is equal to 0. So that equation becomes the following. Like so. And if you look at it carefully, you'll notice that the only unknown is the time t. There are going to be two answers for the time t because this is a quadratic expression. Now in part B of the problem, on the left-hand side, recall that this was a 0, and then therefore solving for the time mathematically was easy to do. Not so in this case, however. In this case, the value of the left-hand side of the expression is equal to 10 meters. So then therefore I'm going to have to use quadratic formula in order to solve for the two times. In order to see how the quadratic formula is going to work, however, let me go ahead and take these two terms here and move them to the right-hand side of the expression. Like so. So take a look at that carefully. And now using the quadratic formula, let me go ahead and write this out for you. The coefficient A is going to be the 1/2 g. And then the coefficient B, including the negative sign, is right here. And then the coefficient C is the constant of 10 meters. That's right here. A, B, and C, recall, are the coefficients associated with the quadratic formula. Okay, let me go ahead now and write out what the quadratic formula is going to look like here. Okay, so first of all, we have negative B plus or minus the square root. I think I'm going to have just enough room here of B squared minus 4AC, and then all divided by 2A, like so. So take a look at that carefully, pause if you need to, and then copy this down. Okay, there is a little bit of simplifying that occurs here in this expression. First of all, in the denominator, the 2's cancel out like so. And then underneath the radical sign, this negative sign here is going to square, so I can ignore it. And then over here, I can cancel 2 here and here, like so. I've neglected, by the way, to write down a g over here. There we go, 1/2 g for that term. Make sure that you make that correction in your notes if necessary. Okay, let me go ahead and plug in my numbers here, and let's begin to see what happens. Okay, so first of all, from earlier, we have 100 meters per second times the sine of 30 degrees. That's a total of 50 meters per second. Okay, and then plus or minus, let me now go ahead and do the radical sign for us. All right, so I'm going to have the square root here. First of all, 50 squared, so that's 2,500. And then minus 2 times 9.8, and then times 10 meters, like so. Okay, and then take the square root of all of that. This turns out to be 48. And then all divided by g, 9.8. Like so. Okay, now if I use the negative sign in the numerator of the expression, this is going to give me the lesser time. This will be the time on the way up. So 50 minus 48, and then all divided by 9.8. And this comes out to be 0.2 seconds. And then the second value is going to be with the plus sign. So that's going to be 98 divided by 9.8. That's a total of 10 seconds. Like so. Once again, there's some symmetry here. You can make a comparison with what we saw earlier in part B of the problem in the following way. So the time from here to here was 0.2 seconds. Time from here to here was 10 seconds. Recall that the time from here to here was 10.2 seconds. So there's a 0.2 second difference between these 2 points and between these 2 points here. Once again, that's hinting at the symmetry that is present. Okay, lastly, we have to find the details here of the velocity vector in green. We actually found v sub x earlier in the problem, if you recall, to be 86.6 meters per second. Recall that the horizontal component of the velocity vector is a constant. Okay, then let's find the v sub y. In order to find the v sub y's, we'll take the 2 times that I just found and then plug them in here into the v sub y equation. So let's see what first of all happens with 0.2 seconds. All right, so v naught sine theta naught, so 50 minus 9.8 times 0.2 seconds. And this works out to be positive 48 meters per second. And now let's see what happens with the time of 10 seconds plugged into the expression. So v naught sine theta naught, so 50 minus 9.8, and then times 10 seconds, and sure enough, this works out to be negative 48 meters per second. Notice that this plus or minus 48 meters per second is the same thing as this number here. That's not a coincidence. The reason for that is because underneath the radical sign right here is actually the third kinematics equation for v sub y, even though we are not using it here directly in the example. By the way, just leaving the components in this form here in describing the velocity vectors v in green is perfectly fine. Okay, now I've been hinting at the obvious symmetry in this problem over and over as I've worked ourselves through it. Let me now go ahead and prove to you that in fact a projectile's trajectory is a parabola. That just takes a few moments. Let me go ahead and erase here to do so. Okay, let me make some adjustments here to my position equations here as I begin. Okay, so here's what we have to do. Prove that a projectile's path or trajectory is a parabola. Okay, so here's then how I'm going to set this up. Okay, right here is the vertical direction, right here is the horizontal direction, and then we're going to launch the projectile here from the origin. So I'm immediately saying, just to keep things simple, that both x naught and y naught are equal to 0. That's why I erased those values here in these two expressions. Okay, and then right here is our projectile, like so. We have to prove that this red curve, in fact, is a parabola. So in order to do so, what I need to find is a specific function that describes this graph, that is y as a function of x. Once I have that function then describes the path here of a projectile. Now, do I have that function? No, I don't, because what I have right here are position equations for y and x that are functions of the time t. They're functions of the same variable. Because they are functions of the same variable, however, this then means that they are parametric equations, and then therefore I could, of course, algebraically combine them together. So let's go ahead and do so by eliminating time t between them. Here's how I'm going to eliminate the time. I'm going to take this horizontal displacement equation and solve for t, and then plug into here and here. Once I do, I will then come up with the expression that I'm looking for. Let's now see what happens. Okay, so divide this here to the other side to solve for time t, like so. And now I take that time and I plug it into here and here. So let's go ahead now and find y as, in fact, a function of x. So I've got v naught sine theta naught, and then times t. Okay, and then minus 1/2 g, and then times t squared. Like so. And I end up with this rather messy looking function, as you can see. It does simplify a little bit, that's fine. Let's go ahead and cancel out a v naught here from these two terms. And then right over here in this term, I have sine over cosine, which is tangent. So let's go ahead and then write the expression like this. Like so. And then this is as far as I have to go mathematically. And the reason for that is because we do have the function that we're looking for, the function that describes this graph. And now take a look at this right here. Notice, of course, that it's a quadratic. It's a function of x squared. So then therefore, if it's a quadratic, this then means that the graph associated with this function is in fact a parabola. The quadratic term is negative, therefore the parabola opens downwards. So we have now successfully proved that a projectile's path is a parabola. Once you have gone through a mathematical proof such as this, and there's really nothing else to say, then what we usually write in mathematics or in physics is QED. QED is a Latin acronym. I think it stands for like quoendo demonstratum or something like that. It basically means it is demonstrated. In other words, we've demonstrated just by getting this far that a projectile's path is in fact a parabola. The sometimes humorous English version of QED, by the way, is quite easily done. Okay, let me go ahead and conclude this portion of the lecture on projectiles here.